Hello everyone and welcome back. Today we're going to talk about the Lorentz transformation again. Actually, probably for the rest of our course we have to deal with this. So the more we get ourselves prepared, the better for ourselves for the later periods throughout the course. So in the Lorentz transformation, so far what we know about it is that it's actually a combination of two different kinds of transformation. One is the familiar rotation and the other is called boosts. Now we have seen the rotation matrices and in the four-dimensional space-time representation, the rotation matrix retains more or less the same form. So for example, a typical rotation about x-axis should look like something like this. So 1, 1, and then we have cosine theta, sine theta, negative, sine theta, and cosine theta. And notice that we are quantifying the rotation by using a parameter. In this case, the parameter is theta. And the range of theta is finite. It can go from 0 to twice pi, or in some other convention, it can go from negative pi to pi. And the fact that the parameter of rotation has finite range will play a very crucial role for us when we talk about the generators of Lorentz transformation or Poincare transformation. As a side note, I'd just like to mention that the Poincare transformation is nothing the Lorentz transformation plus translation. Notice that we have left out translation in our discussion the whole period. If we include the translation, then the Lorentz transformation is called the Poincare transformation, and that describes the whole physics of space-time relativity. Nevertheless, we have Lorentz transformation, which is a combination of rotation, and as we know, rotation can take place in three independent pair of planes. So there are three possible independent rotation and three possible direction along which you can carry out your boost. So there are also three independent boosts. Now, the way we have written our representation of boosts is as follows. So boosts along the x direction, let's just say, was written as gamma, gamma beta, and gamma, 1 in the rest of the diagonal entries, and 0 in the rest of the places. And then we want to ask ourselves the question whether it is possible to write the representation of boost matrix in an analogous way that we have written the representation of the rotation matrix. And the answer is yes. And although there is some sort of analogy, understandably it will not be the same kind of functions or in fact the same parameter, because rotation we know has finite parameter range, finite range for parameters, but for boost we'll expect that whatever the parameter is, it will have an infinite range. And so the best candidate to represent the entries by a function is to use the hyperbolic trigonometric functions, which we write as cos phi or cosine hyperbolic phi and sinh phi or sine hyperbolic phi and so on. So let's take gamma, which is 1 over square root of 1 minus beta squared, as cos hyperbolic phi. And I notice that using the identity cos phi whole squared minus sine hyperbolic phi whole squared is equal to 1. And then if we plug it in, we have sine hyperbolic phi squared is equal to 1 over 1 minus beta squared minus 1, which will give us beta squared divided by 1 minus beta squared, which is simply gamma squared beta squared. And so, using this, we can rewrite our expression for the boost matrix by writing cos hyperbolic and sine hyperbolic as the entries, and then the matrix would look something like this: cos hyperbolic, sine hyperbolic, sine hyperbolic, cos hyperbolic. And notice that, as expected, phi in the hyperbolic trigonometric functions does have infinite range, and it ranges from negative infinity to positive infinity. And this parameter is called the rapidity parameter. This is a valid representation because after a Lorentz transformation, I would still want it to be considered as a coordinate transformation because I don't want the units of measurement to change because of changing a reference frame. So if I take determinant of lambda rotation along the x direction, this is simply 1 because it will result in cosine squared theta minus sine squared theta. In a similar way, the determinant of lambda boost along x direction is also 1 because we have cosine hyperbolic squared phi minus sine hyperbolic squared phi, which is 1. So there is the promised rapidity parameter. For the next stop, I'd like to talk about the objects on which the Lorentz transformation matrices work, which is basically the four vectors. And under the Minkowski metric, eta mu nu, which has the signature of 1 and -1, -1, -1, as we have chosen a convention for this course, we notice the inner product of two four vectors can be written as a mu. So there is a contraction because after the inner product you want to get a number. And so if we write it explicitly by using this metric, it's simply this: eta mu nu, a mu a nu. And if you write it explicitly, you get a0 squared minus a1 squared minus a2 squared minus a3 squared. And as we know, this scalar quantity should be invariant under coordinate transformation. But in Minkowski spacetime, the coordinate transformation matrices are simply Lorentz transformation matrices. So under Lorentz transformation, we would expect this quantity to be invariant. So for example, if we have x mu, then it is simply c squared t squared minus x squared minus y squared minus z squared. That means this quantity should be invariant. This should also be the case for other four vectors. For example, if I take the momentum four vector, then p mu should give me e squared divided by c squared minus px squared minus py squared minus pz squared. Now let us dig a little bit deeper. So as we expect, a mu under a Lorentz transformation should give us a prime mu contracted with a prime mu. Now since these two indices are contracted, I can rewrite them as a prime nu, and using the metric I can write eta mu sigma and then a mu a sigma, and on the right hand side we have eta prime nu rho a prime nu a prime rho. Under the Lorentz transformation we have eta prime mu rho, and instead of a prime mu we write lambda mu nu a mu, and instead of this one we write lambda rho sigma a sigma. And I notice that from this we can deduce the transformation of the metric, and we have lambda nu mu, lambda rho sigma, eta prime nu rho, which is exactly the way we expect the metric to transform under Lorentz transformation. I'd just like to end by stating one obvious thing. It is the inner product of the energy momentum tensor with itself. And as we have just seen, it is explicitly written as E squared divided by C squared minus Px squared minus Py squared minus Pz squared. And this I can write simply as E squared by C squared minus P3 vector whole squared. Now, we expect this value to be conserved, to be invariant under Lorentz transformation. So if we jump onto a reference frame in which the particle is at rest, then its momentum part is 0, so 0 squared, and its energy part is mc squared whole squared divided by c squared, because of the invariance of this particular contraction under Lorentz transformation. So from this, we can say that E squared divided by C squared minus P squared is equal to M squared C squared, from which we get a familiar relation E squared is equal to PC squared plus M squared C to the power 4. So by this video, I am pulling an apparent rest to the discussion of special relativity. If we need some further information or further discussion about special relativity in future, I'll do that. And I think after 7 videos on special relativity, it's a good place to stop here. In the next stage, we'll be discussing about Lie group and Lie algebra, and eventually, hopefully, if we can get through that, the latter part of the course will be coming. So far, I have maintained this custom of 2 weekly videos, 2 videos a week. I hope I can continue in this manner and do some sort of benefit to you, the audience, and some sort of justice to the subject. For any discussion or question, you can text me, you can contact me in my social media. I have put all the links in the description. See you later.